I think we will start, so the speakers will be. Zapraszamy. So yeah, we will start in a moment. Right now.
We don't see your screen anymore.
Oh, we close it, okay?
You don't see my screen anymore?
No. Oh, wait, sorry. Yes, it is there. That's new Zoom. Sorry. It's all fine.
So good afternoon, everyone. Today we are having a remote talk by Jan van Roestel from the University of Amsterdam. Jan was doing his PhD in Nijmegen, or however we pronounce it in the Netherlands, and then he moved for a postdoc to Caltech, working at ZTF Data, and that's where I believe he met with Przemek. And currently he's working at the BlackGEM projects, and so the floor is yours, Jan.
Right, thank you. Yes, I'm would have loved to be there in person, but sadly it didn't work out. Thank you for inviting me, though. I actually am very eager to talk about the things I'm working on now and the things I've done. And I couldn't choose, so I decided to talk a bit about both. But the common theme in my work is really searching for gravitational wave sources using optical survey telescopes. So I'll first go into an outline of my talk. So I'll give an introduction into gravitational waves and optical counterparts of those gravitational wave sources. And then talk about some work I've done with the Zwicky Transient Facility. For the most part, is to study white dwarf binary stars, specifically white dwarf binary stars that are gravitational wave sources or are where the evolution is driven by gravitational wave emission. And in the last part of my talk, I'll talk about the work I'm doing now with the BlackGEM array, which is an optical survey telescope specifically designed to follow up gravitational wave sources. Right. So let's start with gravitational wave sources. What are they? Well, actually tried to find a good explanation for this, and I actually looked at the LIGO website, and they had a very nice description. Gravitational waves are ripples in space-time caused by some of the most violent and energetic processes in the universe. And I could not word that better, so I thought I'd use the quote directly. But yeah, you can imagine the gravitational waves are basically waves in space-time that have, well, they can be stochastic, but often they are periodic, as in they have a typical amplitude, frequency, polarization. They move through space at the speed of light, and very importantly, they carry energy and angular momentum. And as we'll talk about later, that energy and angular momentum has to come from somewhere. But basically, these waves travel through space-time, slow or very causing very tiny compressions or stretches of basically distances, and that's something we'll see later as well. So actually, one of the first detections, or I guess indirect detections of gravitational waves, were already done in sorry, I don't know the year, but what was done with using the Roestel pulsar, and they got the Nobel Prize in 1993 for this. And these gravitational waves were detected indirectly, and this was done by very precisely measuring the orbital period of a binary neutron star. So you've got two neutron stars orbiting each other. because one of them is a pulsar, you can very precisely time the orbital period of this binary. And what the observers noticed there is that the orbital period was slowly decreasing, as in the period became shorter. And it became, and this observation was perfectly consistent with predictions from gravitational waves, as in these sources, they emit gravitational waves. These gravitational waves carry away energy and angular momentum. And as I already mentioned before, this energy and angular momentum has to come from something. And this, in this case, it comes from the binary orbit. And that is what these people observed here, and their measurements are perfectly consistent with the gravitational wave prediction. Of course, things got even more exciting in 2015 with the direct detection of gravitational wave radiation. For decades now, physicists and engineers have been building these large laser interferometers with the goal to measure gravitational waves passing through the Earth. And they do that basically by very precisely measuring distances. So if you have these laser interferometers, you can very precisely determine if the distance between your source and your mirror at the end changes. And that's what's been done on a very large scale. On the lower left, you see one of the LIGO gravitational wave interferometers. I think the arms are about 3 kilometers long. And in 2015, these interferometers detected the first gravitational wave signal. And that's what you see on the right-hand side. They measured, in this case, the signal of two black holes orbiting each other, getting closer and closer. Again, gravitational waves carry away energy and angular momentum from the orbit, so objects in a binary get closer and closer together, and at some point they touch each other and merge. And that signal was detected by the gravitational wave detectors. And I think got a very nice animation here to show that. So you've got, in this case, 2 black holes orbiting each other, emitting gravitational waves and slowly spiraling inward. So the orbital period is slowly decreasing and decreasing up to the point that the black holes touch each other, which is something we're getting to in about now. And now the 2 black holes have merged together, resulting in a single black hole, and the source has stopped emitting gravitational wave radiation. So I think there's 2 things to remember here, that the strongest gravitational wave signal you'll see will be during the merger event. So really the very last little bit of the merger event will be the strongest gravitational wave signal, kind of a burst you can think of. However, this source will be or had been emitting gravitational waves for millions and millions of years. So you can imagine that these binary stars start out in a very wide orbit, and as they slowly spiral inwards, orbiting each other for millions of years, they are basically emitting gravitational waves for these millions of years. And both these these persistent sources, but also these final merger events, will be detectable by gravitational wave observatories. So, no, I don't want to see this again. Sorry. Right. So we want to talk a bit about the astrophysical sources of gravitational waves. And again, quoting from the LIGO website, gravitational waves are generated by a time-varying quadrupole moment. I did reword this a little bit. I think mass that accelerates generate gravitational waves. So basically, if you've got something that is accelerating, as in a binary, I mean, a rotation is a constant acceleration around the center of mass. That causes the emission of or generation of gravitational waves. And of course, one of the prime sources or astrophysical sources of these gravitational waves are binary stars. And just to give you a sense of how strong the gravitational waves are, I've written down the gravitational wave energy loss of a binary star. It's 2/5 times g to the power 4, the total mass to the power 5, divided by the semi-major axis to the 5th power. And I think what's important to remember is that you need something that has a lot of mass, and you need a binary that is very, two stars with a very small semi-major axis. And this goes to, well, to the 5th power. So you really want to have very, very tight binaries and very massive binaries. And of course, as we've already seen in my previous slides, sources are black holes, of course, but also neutron stars. They're also massive enough and close enough together to be able to emit detectable gravitational waves. However, I would definitely like to talk about the white dwarf binary stars, which are also compact enough and close enough to be able to emit detectable gravitational wave radiation. Just for completeness, I've also added a few, the category of others. There are definitely other sources of gravitational waves. You've got primordial gravitational waves from the Big Bang. There's predictions that supernova explosions, so exploding stars, which are very likely asymmetric, could also cause gravitational wave emission, or rotating neutron stars, where the neutron star might not be completely symmetric. That could also be a source of gravitational wave radiation. However, I think by far the most interesting and dominant source are the massive compact binaries. I'll talk a little bit more about those. So I guess one other thing I like to emphasize here, that not all gravitational waves are the same. I mean, it is the same phenomena, like photons are, all photons are the same in a sense. However, as you can imagine, as in with photons, you've got X-rays, but you also got radio waves and everything in between. And for gravitational waves, you can also have very different wavelengths of gravitational waves. Very high frequency gravitational waves with of multiple hertz to millihertz, or even much lower, like 10 to the minus 16. The scale here goes. And depending on the frequency, you both have different ways to detect them. So the very long period, low frequency gravitational waves, you really really need very long baselines. For example, using pulsar timing, where you measure the distance from the Earth to a pulsar, and you actually you check if there's any change in distance there to detect very long wavelengths gravitational waves. However, as we've already seen, you can also use very tiny, much smaller interferometers, like the LIGO Virgo detectors, which have arms of 3 kilometers to detect much higher frequency gravitational waves. And in between, there's also the proposed LISA gravitational wave detectors, which will be basically will use 3 satellites shooting lasers between the 3 satellites to detect the more intermediate frequencies. And I'll get to that later on in my talk. Excuse me. And that way you can basically cover the entire spectrum. Of course, I already mentioned that the frequencies of gravitational waves are very different, and that those are also generated by all kinds of different sources. As I mentioned, you need something to have something detectable. You need to have massive objects in a binary which are close together. So actually, as an exercise for myself, I actually calculated what is, depending on what type of astrophysical source, what is the shortest period you can fit them in. So, for example, if you take two Sun-type stars, you can fit them in an orbital period of about 9 hours. If you would put them closer, they would basically start to interact and either merge or transfer mass. Brown dwarf stars are much more dense than the sun, and you can fit them in a much smaller orbit. So you can fit them in an orbital period of 1 hour. So if you have a binary like that, they would generate gravitational waves with a period of 1 hour. However, the brown dwarfs are not massive enough, and they're probably still too far out to detect or to generate any detectable gravitational waves. Now, I think that the fun starts with the white dwarf stars. They are compact enough that you can actually put them in an orbit, which is just 1 minute. That is quite extreme. I think the shortest period double white dwarf is 5.4 minutes at the moment. But really, that's the time scale you have to think of. And that is close enough that, and white dwarfs are also massive enough that you can actually generate gravitational waves that should be detectable with the technology we currently have. Of course, neutron stars and black holes are even more compact than white dwarfs, and you can put them much closer together. They're more massive, and therefore they are also definitely detectable gravitational wave sources. So the title of my talk is about gravitational wave sources and optical survey telescopes. So I'm now gonna leave the sources behind which either do not generate gravitational waves like main sequence stars and brown dwarfs. And I'm also not going to talk more about black holes because in principle they don't emit any optical light. So for the rest of my talk, I'll focus on the white dwarf binaries, which mean they emit light, so you can see them with optical survey telescopes. And in the second part, I'll talk about neutron stars. Although neutron stars themselves, they don't emit any light. If you actually merge them together, they cause an explosion, and that is something we can detect with survey telescopes. Right, so let's talk a bit about white dwarf binary stars and gravitational waves. So this is work I've done mostly when I was at Caltech, and I've continued doing. And excuse me, just to remind you that white dwarfs are typically half a solar mass. They can be lower mass or higher mass. They are roughly the size of the Earth, so much more compact than a main sequence star, but not as compact as a neutron star or black hole. But why I like them so much is that there are actually quite many of them. 95% of all stars end up as a white dwarf, and if you look at the space density of white dwarfs, actually 1 in 30 stars is a white dwarf. If you just take some volume, some local volume, you would actually find quite a few white dwarfs in there. Right, so you can see I mean they're not very big, but you can find many of them in the galaxy, and that means you can also find lots of rare configurations of white dwarfs. And before we talk about the white dwarfs, white dwarf binaries, we need to first look into main sequence binaries. As you probably know, many stars are not born as single stars, but they are born as doubles, binaries, triples, quadruples, or multi-stars, higher multiple star systems. And if the distance between the stars is very large, they do not interact. However, if the orbital separation is small, you can get all kinds of interactions. And I think this is just an overview of a way to make all kinds of white dwarf binary stars, where you start out with two main sequence stars. If the stars are close enough together, they will form or go through a common envelope event where they share an atmosphere temporarily. This atmosphere gets rejected while the two stars gets closer together. And after this phase, you basically have the core of your first star left over, and that is basically what a white dwarf is. And then you can continue this evolution of this binary system by either having another common envelope, and that's the way to create two white dwarf stars in a tight orbit. Or you can have stable mass transfer. That way you get a so-called cataclysmic variable. Or you can get, if your secondary star is a bit more evolved, you can get a helium star and then start mass transfer, and those are called AM-CDN systems. This is a very schematic depiction of what can happen with these binary interactions, and it's definitely not complete. But these are, I think, the most predominant channels. And also, there's a lot of different final stages. For example, once you've got these two white dwarfs, they will emit gravitational waves and merge together to either form a 1A or merge into a single white dwarf. I think one of the speakers from last year talked about rapidly rotating white dwarfs. So that's how they fit in this white dwarf binary evolution scheme here. But you see, there's also a lot of question marks here. So we don't really understand what combination of white dwarfs, binary interaction results in which final outcome. So, basically all the objects I've circled here are in very close orbits and are gravitational wave sources. So what I'll talk about in the next few slides is actually how we try to find these sources to better understand the evolutionary picture that I've shown here, but also better understand what the final outcome is of these different interactions and channels. Just putting it in a slightly different way, or more of an observer figure, I guess. So I really like this figure, so I'll spend a little bit of time to talk about it in a bit more detail. On the x-axis here, you have the orbital period in minutes. So on the left side, it's about 10 minutes, and the right side of this figure is about a few days. And on the y-axis, you've got the accretion rate with the two gray boxes at the bottom, no accretion. And this figure shows an overview of all the different kinds of white dwarfs that you can find in the galaxy, or at least the ones we found so far. So just starting with this gray box, these are the white dwarf main sequence stars, typically white dwarf red dwarf stars, because they're easiest to find. And you see that they basically exist from periods of a few days going down to about 100 minutes. And that is, of course, again, because the density of a main sequence star is not large enough to fit in a smaller orbit. Then up here, you've got the accreting systems, the white dwarf, red dwarf systems where there's mass transfer, also known as cataclysmic variable stars. And they actually undergo some quite complex evolution. This is also something I'm very interested in, but I'm not going to talk about today. Now, the region I want to focus on is really the region here. Basically, the sub 1 hour region. So the white dwarf binaries which have periods of about 65 minutes or less. And there's basically two kinds. You've got the detached systems, which are shown also on the figure on the right, where you've got just two white dwarfs orbiting each other, not interacting, except they are emitting gravitational waves. Of course, as we know, is that white dwarfs are not very massive and the orbit is relatively large. So the amount of energy and angular momentum lost by these white dwarfs is not very large. However, if your white dwarf binary has a period of 12 hours, it will very slowly spiral inwards and merge together within 1 Hubble time. So you basically have all these systems about 12 hours. They will very slowly move to the left of this diagram, and then as they get to an orbit of a few minutes, the white dwarfs will start to interact, and then something will happen. Either they will merge together, or they will explode as a supernova 1A, or you can have stable mass transfer, and that's what's also shown on the top right here, where you've got a low mass white dwarf transferring material to a higher mass white dwarf. And they actually, because of this mass transfer, they actually evolve outwards again. So they basically go from a detached double white dwarf to a very high accretion rate, and then very slowly evolve to longer periods again, while the accretion rate slowly decreases. We're only really scratching the surface of this part of this phase space. We still don't quite understand how this all works, and basically what combination of white dwarfs you need to get to the different outcomes. And that is one of the motivations also to find more of these objects, to better study them and understand how these gravitational waves bring these sources together, what the final result is, and also if you have stable accretion, how the interaction between gravitational wave losses and mass transfer interact to cause these objects to increase their orbital period again. So with the background picture out of the way, I'll talk a bit about a few specific objects and how to find them. So I've mentioned the Roestel pulsar at the very beginning of my talk. That was the neutron-star system, for which they measured the change of the orbital period. In 2012, Hermes et al. Did the same for a white dwarf system. And in this case, they actually used the fact that this was an eclipsing white dwarf binary. And because this white dwarf binary was eclipsing, you can very precisely time when the eclipse happens. And that is what they use to very precisely measure the change in the orbital period. So here on the figure on the right, you see the light curve of this double white dwarf. And the figure below shows basically that the eclipse will arrive earlier and earlier if you wait a few years. So the difference between the red curve here and the purple curve here is about 1 year difference, and you see that the eclipse is now 6 seconds earlier than you would predict without gravitational wave losses. And actually the reason why we want to study these objects is not only because they are gravitational wave sources, it's also a very useful way to study the structure of white dwarfs, because as opposed to neutron stars, white dwarfs are much bigger, and that's why you also get tidal effects, and that could also cause the orbital period to change. So these systems are also not only interesting from a gravitational wave standpoint, but also from a white dwarf structure standpoint. So this one was studied in 2012, and we're very interested in finding more of them with basically white dwarfs across the mass range from 0.15 to as high as we can find them, 1.4 if possible. And that's something we were very eager to do, but the thing is, they're very rare. So one thing, the challenge we have here is really, with Gaia, we now know where all the white dwarfs are. They're basically in the bottom left of the Gaia magnitude color diagram. However, that still leaves a few 100,000 candidates to look at. You can typically tell from the absolute magnitude that something is a white dwarf, but it can be quite hard to tell a double white dwarf apart from a single white dwarf just based on the luminosity. So the challenge we had is that, well, we know that these things are either white dwarfs or double white dwarfs, but how can we actually identify the double white dwarfs from this sample, which are maybe a few dozen? And the difficulty is also that these things are basically all over the sky. I just made a histogram just to understand this better myself. But basically, if you look at a square degree, you typically find, let's say, 8 plus minus a few white dwarfs in that region. There's a small overdensity towards the galactic plane, but actually that difference is the difference between looking outside of the galaxy or inside the galactic plane actually doesn't matter that much. And the reason is, of course, that these white dwarfs are all very close by, so you're really not sensitive to the mass distribution of the galactic disk, because we're really looking at a very local volume here with these white dwarfs. So, and that's what I used the Zwicky Transient Facility for. The Zwicky Transient Facility is basically a huge camera which measures the brightness of stars every night. And of course, these binaries, especially the eclipsing white dwarf binaries, they show a periodic signal on their orbital period. So, oh, sorry, before I go to that, let me briefly show how ZTF works. It's, by the way, a fully robotic telescope. And I think it's this image was, video was shot during twilight, so I'm not sure how useful this data is. But it's basically a fully robotic telescope. There's no human in the loop here, and it has been for about 6 years now, been operating like this, observing the night sky every night. It has a field of view which is large enough to basically cover the entire visible sky once a night, but it uses 2 filters, so it actually observes the entire night sky every 2 nights, but it does it in 2 filters. And well, that's resulted in a huge data set, especially or including light curves of white dwarf stars in the northern hemisphere. And the challenge we have here is, well, we want to find more of these double white dwarfs, especially eclipsing double white dwarfs, because those are the ones we can use to study orbital period changes, and in addition to that, we can use the eclipses to also study the masses, radii of the stars. So the signature we're looking for in this huge data set of white dwarf light curves is any short period signal. There's multiple ways to do that. I really focused on using the Boxley square method, which is well designed to find exoplanet transits, but it's also very useful to find eclipsing double white dwarfs. And that's something I applied on the ZTF dataset, and that's been quite a gold mine, I would say, with very interesting white dwarfs of all kinds that we found there. So let me briefly talk about a few of them. So I'll start with the detached double white dwarfs. This is work done by my collaborator Kevin Birch in 2019. And after only 3 months of observing with ZTF, he already found what I think is still the most interesting source, double white dwarf source found with ZTF. And this is a binary star, a white dwarf binary star with a period of 6.9 minutes. So a very short period, almost half the orbital period than the first double white dwarf gravitational wave source that was studied. And for this source, Kevin Birch was already able to measure the period change after a few months, and that's something that's shown here. And using archival data, he basically could measure the change in the eclipse arrival time to 2,500 seconds in about 10 years. So if you remember the previous one I mentioned, that one had a period change of just 6 seconds in 1 year. This one shows a eclipse arrival time change of 2,500 seconds in 10 years. So this one is a much stronger gravitational wave source. And very interestingly, this is also a gravitational wave source that will be very strong a very strong source for the LISA gravitational wave detector, which is going to be launched in 2034, and that's shown on this part of the figure here, where this shows the gravitational wave strength versus the gravitational wave frequency. And you see that this source, GTFJ 1539, is one of the strongest gravitational wave source predicted to be found by LISA. So we were all very excited by this discovery, and we definitely doubled down on our efforts to find more of them. And we definitely found more of them, but none of them had a short period like this one. But you basically see there's basically a whole array of different types of double white dwarf eclipsing binaries here, periods from 7 minutes all the way to 256, and you see that the light curves are quite diverse. That's really because the radii and the luminosity ratio between the white dwarfs is very different. So this is a very diverse sample to study, and that's something we're still looking into further. What are the properties of these white dwarfs that have these short periods, and can we determine what the masses are and how soon they will, or how strong of a gravitational wave source they are, and how soon they will merge. Right. So then I'll move on to the accreting systems, which are really my favorite type of white dwarf binaries. And basically, as I mentioned before, these systems used to be some kind of white dwarf system. However, when they came into contact after decreasing their orbital period and losing angular momentum, they somehow survived this encounter and started stable mass transfer, where the donor is donating material to the primary star, and the orbital period is actually increasing again. It's still driven by gravitational waves, but because of the mass accretion, actually the total effect of this gravitational wave angular momentum loss is that the binary increases in period again. And so that's also something we've been looking at using the same method, finding again short period signals in the Zwicky Transient Facility data. The interesting thing here is that these donors are actually very cold. So if you look in optical wavelengths, they're completely dark. So what the signature that you see is that the smaller primary white dwarf disappears behind the very dark donor, and that's where you typically get very deep eclipses. So this is the ZTF data in the G, R, and I band, and you see here that every 50, I think this one's 35 minutes, this one's 62 minutes, and orbital periods in between. You see that every orbital period you get a very deep eclipse where the white dwarf basically completely disappears. And this has been very useful because one of the issues with these AMCVM binaries, so the accreting white dwarf systems, is that so far we've found them mostly because of their accretion. The accretion, they have accretion disks and they show outbursts, or they are X-ray sources. However, it proved to be very difficult to study them further, because if you see the disk or you just see an outburst, you can't really measure the masses and the radii of these binaries, or of these different components in this system. So that's why these eclipsing systems have been very useful. There was one other known, but with CTF we found 5 up to 2021, and I think we're reaching about. We're definitely at 16, I think, at the moment. Still finding new ones even after 6 years. Yes, and but that's something I want to briefly talk about as well. Even though these systems only show one eclipse and you've got an accretion disk, there's a lot of information you can get from this. Where you've got in the eclipse basically is a combination of the white dwarf disappearing behind the donor star. You can also see the accretion spot where material flows from the donor to the and hits the white dwarf disk that emits light, and of course the eclipse from the disk itself. You can try to model all this, and that basically with the light curve you can basically solve the entire system. So you get masses, radii of both the white dwarf and the donor star, and that's something that's been proven very useful to understand what is the actual formation history of these systems. I'll just skip that slide. And that's something I've plotted here. So on the left, you see the diagram of the different ways to make AMCVN stars. There's actually 3 possible scenarios here. And on the right-hand side, you see the figure of on the y-axis, the radius, on the x-axis, the mass of these donor stars. And the different models here with the dotted lines, the dashed lines, and the dot dashed lines show what the prediction is for these 3 different channels. As you can see, we're slowly populating this figure. The error bars are sometimes a bit larger than we would want, but we're definitely trying to improve that just by getting higher precision light curve data. And really, the goal of this project, it's still an ongoing project, is to find more systems specifically at shorter periods. So the right-hand side of this figure, and the other goal of the project is that I'm working on is to decrease basically the size of the error bars. And of course, the scientific goal here is to really determine which of these formation channels is the most important one, or can you make accreting white dwarf systems like this through all these different channels. And I think I'm just going to skip this one. The final slide on the white dwarf binaries is this one. This is work done by my collaborator Thomas Kupfer. So he has collected, or he has made an overview of all the different white dwarf binaries in short orbital periods, taking their distances, measured masses into account, and then calculated what the predicted gravitational wave strain is that will be detectable by the LISA satellite shown on the top right. So the LISA satellite will be launched in 2034, but as you can see, we're already studying the sources. We're already doing LISA gravitational wave science today. And the reason why we're so interested in these white dwarfs is that both the detects and accreting white dwarfs are the most prominent LISA sources, or most numerous sources that LISA will detect. And by studying them already, we can, whenever LISA is turned on, we can basically test and very well study what we see in the optical and connect that to what we detect in the gravitational waves. And the combination of those two, of course, you've got a very precise localization, distance, period measurements, and by combining that information, you can very precisely measure the properties of these white dwarf binaries. Right, so I have about 5 minutes left, I think, a little bit more. So I briefly want to talk about the project I'm working on now, and that is is doing gravitational wave astronomy with the BlackGEM array. And the BlackGEM array is currently an array of 3 telescopes. It's a project led by the Radboud University in the Netherlands, but the KU Leuven from Belgium is also involved, and other Dutch universities as well, via the NOVA Institute. However, these are the core members. We definitely have collaborators from all over Europe, the US, Chile as well. So it's a very much an international collaboration. So, as I mentioned already, you can not only study white dwarfs using gravitational wave sources which are white dwarfs, but also neutron stars. When neutron stars merge, they cause an explosion, a kilonova, and that's also something you can find in using an optical survey telescope. And I think in the view of time, I'm also going to skip this one. So as we've seen with in 2017 with GW0817, is that if you have two neutron stars that orbit each other, and the orbital period basically gets so close that they merge, you get a very strong gravitational wave signal, as is shown here. This chirp signal here from the LIGO-Virgo gravitational wave detectors. But you can also see something which is an explosion, and that is what was called Astronomical Transient 2017 GFO. And that was a transient, an optical transient that many people looked for. I mean, of course, the LIGO-Virgo detectors, they notified astronomers that they found a neutron, emerging neutron star, and many astronomers used their telescopes to search the region of sky where this emerging neutron star was supposed to happen. And as you can see here, after about 10 hours, the explosion was found near this galaxy. Just gonna skip this. So that is the main goal of BlackGEM. BlackGEM is really dedicated to this step of basically searching the area that LIGO, Virgo, and other gravitational wave detectors say there should be a neutron star or a neutron star black hole merger, and try to find the optical counterpart of this merger. And of course, that is crucial if you want to study these kilonova further with big telescopes like the VLT. And BlackGEM is really designed to fill in this step in this whole chain of finding and studying the kilonova. So you need so with this in mind, the telescope was designed to cover a large part of the sky. And do that quickly. So the field of view of a single BlackGEM telescope is 2.7 square degrees. It has a 110 megapixel single CCD, so that's really quite a large piece of hardware, as actually seen on the bottom left here. And it also includes a filter wheel, because these kilonova have a very particular color and color evolution. And so that was another thing identified that would be very useful to have, is if we not only can find find all the transients in an area, but also if we could study the color evolution of them. That would be very useful to identify the kilonova from regular 1A supernova or other kinds of astronomical transients. So the BlackGEM telescopes are located in La Silla in Chile. You see two of them in the figure in the middle. The third one is just on the left, I think, being built there. They have been there actually since 2020 already. We had a little bit of an issue with COVID, but after we could travel to Chile again, we refurbished or did some maintenance on the telescopes, and they have now been in operation for about a year now. And of course, that is this is one of the images, single images of one of the telescopes, and you can see that it covers a huge part of the sky, and there's lots of stars in there to be studied. I'm just also gonna skip this. Yeah, so the thing I want to talk about is that the LIGO, Virgo, and Kagra gravitational wave detectors, they operate in campaigns. So they basically search for gravitational waves for about 1.5 years now, and then they go offline for an extended time to upgrade the detectors, and then they turn on again to search for to basically search further away and with more sensitivity. So we're now currently in this part of their schedule, which for BlackGEM is very good, because we have now 3 operational telescopes, and we're very eagerly awaiting signals from LIGO and Virgo to start searching the night sky. LIGO and Virgo, by the way, will still do this until February of this year, so we still have a few months ahead of us to find these kilonova. Just to show an example, in April 22nd, we had the first exciting trigger, I would say. A neutron-star black hole event with a 99% probability was detected. The luminosity distance is 188 megaparsecs, which is not as close as the first neutron-star merger, but at this distance, we thought we could maybe detect it. And the area we had to search with BlackGEM is 258 square degrees. So that is actually 99 pointings with BlackGEM. So that's something that actually went very well. BlackGEM was triggered fully automatically within, I think we were on this part of the sky within 10 minutes, maybe even quicker. And the telescope responded fully automatically without any human interaction. Of course, we were alerted that the telescope was going to chase this event, but this worked out not completely flawless, but it went mostly as expected. Sadly, we did not find any counterpart. The reason is that it was full moon, so I think the moon was like 20 degrees away from this region. And also this region is basically, well, the kilonova was possibly behind the galactic plane, so there was also a lot of dust. Yeah, it's a bit disappointing, so we're hoping for some new neutron-star or neutron-star black hole merger events in the next few months that we can follow up with BlackGEM. But the good news is that basically everything worked as we hoped. So let me quickly wrap up. So whenever BlackGEM is, BlackGEM is waiting for a trigger from LIGO Virgo now, but of course we are observing the sky to do other science. And one of the things now we're doing now is first tiling the entire southern sky to get reference images. And in the process, we actually are finding lots and lots of transients which have been missed by other surveys. I think this shows the sky location of them. I think the red points are the detected transients, which are also found by others. But the yellow points are transients that BlackGEM found, which were not yet discovered by other surveys. So there's, even though there are other surveys also doing this in the southern hemisphere, we're still definitely not complete, even if you combine the data from all the discoveries from all these survey telescopes. In addition to studying gravitational wave sources, you can basically do a lot of other science with BlackGEM. I would call this optical time domain astronomy, where we basically have solar system objects, stars from the Milky Way, and transients from beyond in our images. People in the BlackGEM collaboration are all interested in these different topics. Just to give you an overview of the things people are doing, of course, we've got the gravitational wave trigger mode. That's the main science driver, but we also do a local transient survey where we target nearby galaxies a few times per night in multiple colors with the goal to find luminous red novae, for example, so low luminosity transients. Or we want to find transients very early, so we can study the very early evolution of, say, supernova 1As when they interact with previously ejected material, for example. Then there's also what we call the fast synoptic survey. If you're familiar with the Vera Rubin terminology, this would be the deep drilling survey, where we basically target one part of the sky, and we basically keep looking at this part of the sky for a few hours straight, taking an image every 60 seconds. And the goal there is really the same as we've done with CTF, to really find short period variables. These include the double white dwarfs, but also compact pulsators, short timescale flares and outbursts, and all kinds of short timescale galactic phenomena. And finally, BlackGEM will, well, we need to build up a reference image anyway, but we basically take an image of the entire southern sky in basically from the near UV to the near infrared in U, G, R, I, Z, and Q. And once this is done, this data will be made available for via the ESO portal for anyone to use. And I think I'm out of time, so I think I'll just end the talk here. Thank you.
Thank you very much. Second. Thanks a lot. Do we have any questions here? Yes. So I was actually wondering, did I understand it well that all the sub-hour white dwarf pairs will be detectable by LISA?
Yes, so I didn't go into the LISA that much, but yeah, so basically LISA will be able to detect I think tens of thousands of short period double white dwarfs. I think it can even detect very short period double white dwarfs up to the small and large Magellanic Cloud, if I remember correctly.
Okay. Any questions from here? If not, Tomek?
Hi, Jan. Can you hear me?
Yes.
I wasn't quite sure what was the conclusion about those newly discovered binary white dwarfs in CTF. Do you measure already the GR effects, the periods change, or and is it ascribed to GR effects only or to the accretion disks presence?
Yes. Yeah, so for this one, we definitely measured the orbital period change, and that's fully consistent with gravitational wave losses. We are also working on the accreting systems as well, and there it's more difficult. For some systems we expected to find a period change already, or an eclipse arrival time change already, but we didn't see it. So that's a bit puzzling, because with the data we have, we should have found it. So somehow there's some interaction between or some physics from the accretion disk that makes the period not or counteracts the gravitational wave period change. It's something we don't quite understand.
And are they both CO white dwarfs in those pairs?
So for these systems, we typically find that at least one of the two white dwarfs is a lower mass white dwarf, so 0.2, 0.3 solar mass. So those would very likely be helium white dwarfs. Why that is, it's not quite sure. I guess it's some kind of detection bias. I mean, a lower mass white dwarf is bigger and therefore brighter, but also have a larger eclipse probability. So I think there's definitely a bias here.
And those have, there is some evidence of accretion disk in those.
No, I think only in a few of them there's an accretion disk present. Most of these are actually detached systems in this sample.
Okay, thank you, Ian.
Thank you, Lukasz.
Well, I have a couple of questions. I have to choose one, maybe. Okay, so let's get back to the Gaia CMD you showed.
Which one? This one or?
Well, one before. Well, doesn't matter really. So, what my kind of question and comment here is that if you have a binary white dwarf, then it is also visible in astrometry of Gaia, right? So I guess most of the white dwarfs you see here, they have well measured parallaxes. It means that there has been probably some cut applied already. So probably the very classical CMDs from Gaia, they exclude all the binary white dwarfs you would potentially be interested in, and then using the binary solution from Gaia or any information on astrometry from Gaia would indicate some candidates of white dwarf. Have you looked at that?
Yeah, so I'm interested in the very short period white dwarfs. So they would be very close together, and I don't think you would see any signal in the astrometry because of that, as far as I can tell.
Well, if we're talking about minutes, then yeah,
The
maybe.
orbital separation is basically a solar radius, so I guess that will be a big challenge for Gaia, even if these sources are just 100 parsec away.
Okay, that's a very good point. So I will just ask very quickly another question. So what's the theoretically expected, the shortest period of
Yeah, so the shortest period system is one system which is accreting, which has a period of 5.4 minutes. I think the theoretical shortest period is, I think it's 1 minute that I calculated. 1 to 2 minutes. It depends a bit on the mass of the white dwarf. Yeah.
they merge or accrete? Okay. Okay. Thanks. Exciting.
So thank you, Jan. I think we are just running out of time, so let's thank our speaker again.
Yeah. If you have any more questions, feel free to email me.